Good morning, boys and girls, and welcome to the first day when derivatives get real. Today we're going to start the chain rule. Alright here, let's start out with this quick example to kind of get us warmed up and ready to go. Okay, we want to take the derivative with respect to x of the quantity 3x plus 1 squared. Right now we've kind of said the only way we have of doing this is by expanding this out and writing it out. We had a problem like this a few lessons ago. And this is what we said we kind of had to do with it, but we're going to quickly find a workaround. Okay, we need to write this twice. I need to go ahead and double distribute, like that. And so now, once, I should be careful with my equal signs here. I guess these are not necessarily equal. Once I've gone ahead and done this, now I can go ahead and take the derivative of this function. And so the derivative of that would be 18x plus 6. Okay. So right now, if we had something like this, the only way of taking the derivative is by expanding it out. Now, that's great for this problem, but what if I were to take this, and instead of having it squared, what if I raised this to the, 10th power? Now would you want to expand that thing? Nuh-uh, I don't think so. So we got to have a better way, and that better way is called the chain rule. Okay, here is the gist of the chain rule. The chain rule says if y equals f of u or u equals f of x, then y prime is f prime of u times u prime. Okay, kind of confusing here. I'm going to understand that. We're going to kind of go over that a little bit more in a second here. But here's what we want to kind of start taking away from our definition of the chain rule, is that the chain rule is going to be used when we have a function shoved inside another function. Okay, going back to the one we just looked at here. Okay, we had the function 3x plus 1 inside the function of, like, say, u to the 10th. Okay, we're going to use this u as our, our kind of placeholder, and it'll allow us to kind of look at these two different functions we're dealing with that are going to be composites of each other. Okay, there's really going to be two different versions of this definition of this rule. We're going to play around with both of them kind of separately and kind of work our way in, the easiest way to take the derivative using the chain rule. So let's go ahead and start with version 1. All right, here's version 1 of the chain rule. If I want to take the derivative of something, dy dx, another way to say the derivative, I'm going to take the derivative of the function y with respect to u, okay? And then I'm going to take the derivative of the function u with respect to x. If I multiply those together, then the du's would kill each other off, and we'd be left with dy dx. So I'm just going to have to take these composite functions and rewrite y in terms of u, and then I'm going to have u in terms of x, and then I can take those derivatives separately and multiply them together. That's what version 1 says. Here's kind of how it looks like on paper. Okay, here's the function that we want to take the derivative of. Y equals 5x squared plus 11x plus 20. Y equals 5x squared plus 11x, all raised to the 20th power. Okay? This is not one you would want to expand out, right? Not so good here. So, I think the hardest part about chain rule when you first start doing it is seeing these composite functions, seeing you really have a function inside the other one. And so that's why version 1 of the chain rule is kind of nice, because it forces us to rewrite this in terms of u's and x's and everything, and so that I can really see the two different functions that are embedded. Okay? So in this case here, I would say, like, the function on the inside that I'm going to set equal to u is 5x squared plus 11x. So that's my function u in terms of x. And then I could rewrite this as y equals u to the 20th. And there's my function y in terms of u. So if I now want to go and find the derivative of this, I'm going to go find dy dx. I'm going to take the derivative of y with respect to u, take the derivative of y with respect to u, that's what that is saying. So if I took the derivative of this, we would get 20u to the 19th. And then I'm going to multiply that by the derivative of u with respect to x. I now need to go over here, and I'm going to find the derivative of u with respect to x, or du dx. So if I take the derivative of this, we get 10x plus 11. So now I'd have to multiply this by 10x plus 11. Now, my only issue with this answer here is I've got u's and x's, so I want to just quickly go back and plug in what u was. U was 5x squared plus 11x to the 19th. times 10x plus 11. And that is the derivative of that function now, and I didn't have to expand everything out and get all crazy with it. Okay? So the beauty part of this is that I'm going to go ahead and take, I can really separate and see the two different pieces, my y in terms of u and my u in terms of x, and take the derivatives of those separately and multiply them together. As always here, when you're done, make sure, go back in the back of the book, check your answer, make sure that it matches what is there. In this case, that is exactly what they have, but always make sure that your answers are matching what's going on with the answers in the back. All right, let's move on to number 2. Okay, number 2 here, y equals the square root of x squared plus 1. And again, this word's kind of tricky. I think you get a function like this, we got to take the derivative. You got to be able to see that there's an inner and an outer function here. All right? My inner function is u equals x squared plus 1. And that would make my outer function y equals the square root of u. Okay? So I've got my y in terms of u, and I've got my u in terms of x's. So if I now want to go find the derivative of this, I'm going to take the derivative of y with respect to u, and then I'm going to multiply that by the derivative of u with respect to x. All right? So dy dx, the derivative of u to the square root of u, almost said there, u to the 1/2. You might want to rewrite it like that so that we can use the power rule, right? So this is 1/2 u to the negative 1/2. That is the derivative of y with respect to u. And then I need to multiply this by the derivative of u with respect to x. And so the derivative of u with respect to x is 2x plus, not plus anything. Derivative of constant is 0, so it's just 2x. So then down here I'm going to multiply it by the derivative of u with respect to x. 2x. All right. To get my final answer, again, I need to plug in for u. So 1/2 u is x squared plus 1 to the negative 1/2 times 2x. This one here I think we can pretty up a little bit and tidy up. If I go 1/2 times 2x, I'm just going to get x. And because that has a negative exponent, that's going to go to the bottom. And because we started in radical form, I probably want to finish in radical form. And so this would be square root of x squared plus 1. And so that would be my derivative, or my dy dx, okay, for this problem. All right, so version 1 of the chain rule is nice and all, especially in the beginning, because it really forces you to see that inside and outside function and write it down. However, as we get better at this and identifying the inside and outside function, we really don't want to be doing that. We really kind of want to move on a little bit quicker and faster than having to separate things into two different pieces like that. So version 2 of the chain rule is what really allows me to do that, and this is more or less kind of what I wrote in the very beginning. But version 2 of the chain rule says what we're going to do is when you have a composite function, f of g of x, you are going to take the derivative of the outside function, and the inside function just kind of chills, and then you're going to multiply it by the derivative of the inside function. Okay? That again is basically that g of x was our u, and I took the derivative of the y in terms of u, and then I multiplied it by the u prime. These are all saying the same things, just written slightly differently. Okay? But when you normally take the derivative of a function using the chain rule, you're going to take the derivative of the outside function first, and the inside is going to stay the same, and then you're going to multiply it by the derivative of the inside. Okay? By the way, we're going to spend 2 days on this. Today's day is supposed to be fairly nice and kind of get us used to seeing the inside and outside function. I'm going to warn you, tomorrow's going to get a little saucy. So make sure you really practice today's chain rule stuff before trying to jump into 3.7b, the second day of chain rule. Okay, I'm going to go back to that very first problem we started with, y equals 3x plus 1 squared. All right, so if I didn't want to expand this out like we did last time, if I wanted to take the derivative of this using chain rule, okay, what I would do is I would take the derivative of the outside function. I'm not going to write it down, but I am going to think in my head, hey, what would my u be? What is the inside function? So the u in this case would be 3x plus 1, right? I'm not going to actually rewrite it. I'm just going to think about it in my head. So if I took the derivative of this u squared, I would get 2u, right? Or again, I'm just going to take the derivative of the outside function, 2 times 3x plus 1 to the first. Then I need to multiply it by the derivative of the inside function, or by that u prime. So the derivative of the inside, 3x plus 1, is just 3. Now, if I multiply this together, I get 6 times 3x plus 1, or we get 18x plus 6, which was the derivative that we said we came up with when we expanded it out. It's just, in this case, I don't know, 50-50 on which one's easier. However, again, if we raise this to the 10th power, I guarantee it's way easier to use chain rule here than it is to, multiply this thing out. All right, let's do a few more problems using version 2. See if we can get a feel for it. Okay, here we go. So I want to take the derivative of y equals x squared plus 2x plus 7, all raised to the 8th power. Again, not one I'd want to expand out. That would be ugly here, right? So I'm going to, again, try to find my inside and outside function. It looks like x squared plus 2x plus 7 is the inside function, right? So y prime equals, I'm going to take the derivative of the outside function. That would be like u to the 8th. That would be 8u, or x squared, plus 2x plus 7. The inside part stays the same, to the 7th power. Then I need to multiply that by the derivative of the inside, or that u prime. 2x plus 2. Okay? And now I've taken the derivative of this. Again, that is the derivative. I might need to, maybe rewrite this some way. I'm going to go check my answer real fast and then see if that needs to be written or not. And I should mention here, because I technically have the derivative, I would check the answer in the back of the book right here. I found the answer. That might be the answer I have in the back. In this case, it wasn't. And again, why do they do some of these things? I don't know. It just kind of depends. But to get the answer in the back of the book, it looks like what they did was they saw that you could factor out a 2 from back behind here. So they took the 2 out and multiplied by the 8 and got 16 times x squared plus 2x plus 7 to the 7th power times x plus 1. Okay. Do we need to do that? Not really, but to make my answer match, it's good to go through that practice. Try to make sure that you can make your answer match the answer in the back. All right, one more and we're done. Okay, last one here. Y equals sine 2 root x. So far, when we found the inside has been something raised to a power, right? Raised to the 8th, raised to the 1/2. That doesn't always have to be that way. The inside might be inside of something like a sine, inside the argument. Or the inside might be in ln x, or it might be in the exponent of, say, e to the x. These are all places that you might see chain rule where that's technically like an inside of something, all right? Where you can have a function in a function. So, moving along with this one, this is my u is inside of here. Y prime equals, I need to take the derivative of the outside function, all right? So the derivative of sine is cosine, and the inside stays the same, so cosine 2 root x. And then now I need to multiply this by the derivative of the inside. And sometimes, if it helps, like again, this one I maybe just do so we can look at. In this case, we said our u is 2 root x. So if it helps you to just jot some notes like this, that's not a bad thing. And then you might write this as 2x to the 1/2 to help you use your power rule. So if I took the derivative of this, I would get x to the negative 1/2. 1/2 times 2 is 1. And then subtract 1, I get x to the negative 1/2. So that would be the derivative of the inside, x to the negative 1/2. And now I could rewrite this, and this would be, cosine 2 root x all over negative, so all over it goes to the bottom, the square root of x. And that's probably going to guess how our answer looks, but I'll check that real fast. And yep, that's exactly how it looks in the back of the book. All right, one just real fast thing. I know I said that was the last problem, and it was, but one last thing to share with you. I just want to give you the general power rule now that we've covered the chain rule. Whenever you see the power rule, this is really how you're going to see it. Okay, so here's our general power rule. When I take the derivative of u to the n, I'd go n, u to the n minus 1, but you got to remember if that u is a function, you have to multiply it by u prime. Okay? Multiply by the derivative of the inside. And that's it. That's our very first day of chain rule. Work on finding those inside-outside function, boys and girls. Tomorrow we're going to come back and get way saucier with this, so be ready.